Hello and welcome. We are back at it again, and by it, we are talking physics. Heck yeah. So now we are on chapter 20, I think, yes. That is magnetic flux in your textbook. That's going to be we're going to be working on page 681 to 682. Problems number 3, 5, and 7. Today is an extra special day for my extra special audience. That's why we're doing 3 problems. So, these problems concern ourselves a lot of plugging and chugging, although if you're under 21, I recommend only doing the plugging part. And these 3 problems are generally just putting them into the formulas. Number 7, they label it as blue, which means it's going to get a little bit spooky, but fear not, I am here to help. So, generally speaking, when we're looking at magnetic flux, we are concerned with 2 things. We're concerned with the area of the loop of wire or surface. Remember that magnetic flux could be the flux going through an actual area, like the loop of my finger right here, or it could be a made-up surface, which is what we'll deal with at number 7. But most often in real-world applications, you'll be looking at loops of wire, which is what 3 and 5 are. So, magnetic flux concerns itself with the area of the surface you're looking at, or usually the loop of wire, you can think of it that way, the area of the loop. And then it also concerns itself with the component of the magnetic field that is perpendicular to the loop. So sometimes the formula will have this and a cosine theta in there, but I never like to just put in the cosine theta because then you might think, well, if they give me an angle, then I can just plug it right in, but that's not always the case. We'll actually see that when we get to problem number 3. Sometimes you'll end up using sine theta. So it's better to just draw it out, not drop your pen caps, and to figure out just which component of it is actually perpendicular rather than just relying on the formula. So this phi right here is our magnetic flux. Magnetic flux, there we are, is equal to these 2 things multiplied by each other. So to figure out our units, which is something that we in physics like to do, if you want to take a moment to see if you can figure it out for yourself, pause right here. And we're back. So the unit of magnetic field is in Teslas, and our area standard unit is meters squared, so our units are going to be in Teslas, meters squared. That'll basically be the units for all of our problems. So now let's get right into it. For problem number 3, we have 3 edge views of a square loop with side length 0.25 meters. And so right off the bat, I've calculated our area because I know we're going to be using it in just a moment. And it's in a magnetic field, a uniform magnetic field, they didn't say that, but that's the case, of 2 Teslas, 2.00 if you're into sig figs, but I'm not. So we're going to calculate the magnetic flux, through the loop, and basically they're going to move the loop around a little bit and then try to trip you up, but nothing's really trippy about it. So, part A, B, and C, this is A, this is B, this is C. Careful with B and beta, try not to get those confused. So with A, it is very simple. The challenging part of all of these is going to be finding the component of the magnetic field that's perpendicular to the loop of wire. But as you can see already, the entire magnetic field is perpendicular to the loop of wire, so we do not have to do any kind of angle work. So the magnetic flux is going to be equal to the strength of the magnetic field straight up, no sine or cosine theta, times the area is going to be equal to 2 Teslas times 0.0625. Sorry if my handwriting is getting a little tight there. That's in meters squared. I'm actually just going to give myself more room. 0.0625 meters squared, and that will give us a grand total of 0.125 Teslas meters squared. Congratulations, you just did a magnetic flux problem. I recommend that you pause and try all of these if you feel that you can once I've read them or once you've read them, but if not, no worries. So, for part number B, we are in the same situation, same magnetic field, and now we've rotated our loop of wire a little bit, so how will that affect what's going on? It's going to affect this be perpendicular, because now a different component of the magnetic field is going to actually be perpendicular to our loop of wire. So, by the way, the blue rectangles are loop of wire, the green arrows are our magnetic field. So, our magnetic field is going through this way, and they give you this 60-degree angle here. And so I want to find, I like to make it so that way it's the magnetic field going into the loop of wire rather than out of. I find that that's a little easier for me. So I use vertical angles here to set this 60-degree angle equal to this 60-degree angle. This arrow right here is just a continuation of the magnetic field. So this whole thing is one magnetic field line. So vertical angles tell us that this angle here is 60 degrees. And then so we actually want this component right here. That's our golden component here. And that will be given by the sine of 60 degrees. So our magnetic flux is going to be equal, actually I'm skipping ahead a little bit. So our beta perpendicular is going to be equal to the sine of 60 degrees times the original magnetic field. So times 2 Teslas. And so our magnetic flux is going to be equal to our beta perpendicular times our area once more. And doing some more plugging and not chugging, because none of you are 21, you will get 0.0625. I'm sorry, no you won't. That is different. You will get 0.108 Tesla meters squared. Cool beans. So now for C, up here, C is really fun because you just get to look at it. Well, the magnetic field lines are going parallel to the loop of wire, and if the magnetic field lines are parallel, that means that B perpendicular is going to be equal to 0, so the magnetic flux is equal to 0. If you wanted to find out the angle between them, if you're doing this sine method, as you rotate the loop of wire, that angle decreases and decreases until it gets to 0. And so sine of 0 is 0, and so that will give you the same thing. If you were following the formula and doing the cosine, you'd get cosine of 90 is also 0. No matter what way you slice it, the magnetic flux going through there is 0. So the general concept that you should realize is that when the loop of wire is perpendicular to the magnetic field, that will maximize our magnetic flux. And then as it starts rotating to becoming more parallel to the magnetic field, that will bring our magnetic flux lower down to its 0 value there. And so this is how you can get a change in magnetic flux simply by rotating a loop of wire. And you're going to start to have flashbacks of that later on as we keep going, because you're going to have to do math with once it's rotating, and that's a lot of fun. So moving on to problem number 5. This has 2 parts, and for those of you who hate math, you're going to like this problem because you don't have to do any math, even though it looks like you do. So, a long straight wire lies in the plane of a circular coil with a radius 1 meter, and so the wire carries a current of 2 amps and is placed along the diameter of the coil. So that is part A. This is our diagram for part A right here. So our coil is this purple pinkish loop here. Our long straight wire is going up like that. Our current is going up. But your current can be going any direction. And you can, when you're determining magnetic flux, you're supposed to pick one direction as positive, one direction as being negative. And so in this case, I'm going to pick going into the screen from my perspective as positive and coming out towards me, about to hit me in the face, as negative. So we are concerned with the area of the loop, which is constant, but we'll deal with that later. Let's look at this perpendicular component of the magnetic field. So as we know, when we have a long straight wire that has a current, if you the current's going up, you put the right hand on the wire and you grip it with curling your fingers around, because we want to figure out the direction that the current carrying wire generates on its magnetic field. So what direction is the magnetic field going? Well, to the right of the wire, over here, it's going into the screen, but to the left, it's coming out of the screen. And so what's important here is that because the wire is on a diameter, it evenly cuts the circle in half, meaning that the amount of flux generated from the magnetic field going into the screen is perfectly canceled out by the amount of flux generated coming out of the screen. And so in this case, right here, the magnetic flux is 0 because the magnetic flux on both sides cancels out. If it were to ask you only the magnetic flux for the left side or the right side, that would be a complicated calculus problem, and you would get a result. So the magnetic flux on the right side equals the magnetic flux on the left side, and because they're opposite, they cancel out. B is a bit different. Now the coil is along the plane of those concentric magnetic field lines that are generated from the wire. So, if that's the case, then the magnetic field lines are kind of approaching the loop of wire. They are approaching parallel to it. So in this case, none of the magnetic field is perpendicular to this loop of wire, and so for that reason, the magnetic flux is 0. So So these two coils of wire both have a magnetic flux of 0, but for different reasons. In A, it's because it canceled out on both sides. In B, it's because it was 0 the entire way around. And it's hard to draw for B, but you have to imagine the concentric circles and how the coil of wire is kind of like a concentric circle, meaning that it's parallel in every possible point to the magnetic field. And because it's parallel at every possible point to the magnetic field that's generated, it kind of looks like C over here. B perpendicular is 0, so the net magnetic flux is 0. I'm going to pause the video here. This is the end of part 1, and so part 2 we will tackle problem number 7.